All right. Yeah, okay. Sorry, I had to make sure the sound was on. Yeah. So let's talk about 10.4. At this point, we in 10.1, we kind of introduced the language of hypothesis testing, and then in 10.2 and 10.3, we talked about hypothesis tests for proportions and means, respectively. So the one parameter that we have left to talk about is the standard deviation. And sure enough, we can also perform some hypothesis tests for the standard deviation. So that's what we'll talk about in 10.4. This will be pretty quick because, you know, at this point, it's the same reasoning, the same logic that we've been through time and time again. 10.5 then is just going to be a summary and a review of all of the rest of the stuff we've covered in chapter 10. And so I'll take a moment in in section 10.5 to talk a little bit, or to give a little more of a summary of the stuff that we've talked about so far. Sorry, have to keep my kids out while I'm recording. So anyway, so let's talk about hypothesis testing on a standard deviation. Same steps as before. Again, you can have a two-tailed, left-tailed, or right-tailed test. So we'll state the null and alternative hypotheses. Then we'll calculate a test statistic. Then we'll use that test statistic to calculate a p-value. These two steps are going to be done in StatCrunch, right? Okay. And then once we have the p-value, we can make our decision. Okay, if the p-value is less than alpha, we reject the null hypothesis, just like before. Let's take a look at an example. So this one says the television habits of 30 children were observed. The sample mean was found to be 48.2 hours per week, with a standard deviation of 12.4 hours per week. Test the claim that the standard deviation was at least 16 hours per week, or per week. So there we go. So we want to test this claim right here, right? We want to test to see if the standard deviation was at least 16 hours per week. That's kind of, well, let's write some stuff down, and then I was going to say that's kind of odd that that's the question that's being asked here. I may have had a typo, but that's fine. We can still work out the problem. But here's why this is kind of strange to me. So the claim that we're trying to test is that the standard deviation was at least 16 hours per week. So we want to know if sigma was greater than 16, right? That's the alternative because that's the claim we're trying to test. The null hypothesis then would be that sigma equals 16, right? Hours. Now, what sample evidence do we have to try to support the alternative? Well, the sample evidence that we have is that the sample standard deviation, S, was 12.4. The problem also gives us some information about the sample mean, but that's not really necessary information. Notice that to calculate the test statistic, we only need to know the sample standard deviation and the sample size. So we don't even need the sample mean. This was just superfluous information that was given. So this is our sample standard deviation. Based on that sample standard deviation, I'm going to say that we are not going to be rejecting the null hypothesis here, right? It's very unlikely that sigma would be greater than 16 when S was only 12.4. But we'll run the test just to be sure. So to run this test in Stat, so this was step 1, right? To do steps 2 and 3 in StatCrunch, we go to Stat, and then variance stats, and then one sample. And then either with data or with summary, depending on if you have data or a summary of the data. So I'm going to go to Stat, variance stats, one sample, with summary, right? I don't have the raw data, I have a summary of the data. When we go there, they're going to prompt us to enter the sample variance and the sample size, I believe. let's pull up StatCrunch just to be sure, just to see what it is that they ask us for. So variant stats, one sample with summary. Yep, they ask for the sample variance. Now, we talked about this when we were going over confidence intervals. However, based on your test results, I would say a few of you have forgotten that the variance is the standard deviation squared. So what they gave us in this problem, S equals 12.4, that's the standard deviation. The variance then is going to be 12.4 squared. And you can enter that in a couple different ways. You could either use your calculator to figure out what 12.4 is, or you can just type 12.4 squared directly into StatCrunch by typing in 12.4 and then caret. The caret symbol is above the 6 on your keyboard. So hold down Shift and hit 6, and then you get that caret symbol. So 12.4 caret 2, that's the variance. And then the sample size is 30. So n equals 30. You'll notice that when they when they state the hypotheses here, they state them in terms of the variance sigma squared instead of in terms of the standard deviation sigma. Well, so we can fix that pretty easily, right? By doing the same thing that we did up here. If we're saying that the standard deviation is 16, then the variance would be 16 squared. So I'm going to say 16 caret 2. Alternatively, you could type 16 squared into your calculator and see what you get, and then just type that number into this box right here. Okay. And then finally, the alternative hypothesis, it needs to be right-tailed, so this needs to go the other way. So we'll go ahead and hit compute. And we get a very large p-value, right? 0.9553. Okay, my dog is going crazy. I don't know why. So crazy, I forgot. 0.9553. Okay. So the p-value is 0.9553. So we can use that p-value to make a decision. Now let's pause for a moment and remind ourselves what that p-value means. What this means is that if we assume the null hypothesis is true, then there's almost a 96% chance that we would have observed the standard deviation that we observed or larger, which is of course not unlikely at all. It's like almost certain to be true, right? It's almost certain to happen. So that doesn't cast any doubt on our null hypothesis. It causes us to believe that the null hypothesis is most likely true. So we're not going to reject it, right? So we'll say, since the p-value is not less than alpha, oh, we didn't even have an alpha. They didn't give us a level of significance. So it says test the claim. We'll say at the 0.05 level of significance. It doesn't really matter what our level of significance is, to tell you the truth, because this is bigger than any level of significance that we would normally use. So anyway, we'll just say, well, since this is not less than our level of significance, we do not reject the null hypothesis. And so in conclusion, we would say at the 0.05 level of significance, there's not sufficient evidence to suggest that the standard deviation is at least 16 hours per week. The standard deviation what? The standard deviation, time watching television, I guess. Was more than 16 hours per week. Right? Not enough evidence to support that claim. Again, obviously, I mean, our sample standard deviation wasn't even 16. It was smaller than that. So not a surprise that we're failing to reject the null hypothesis on this problem. Okay, but there's that one. Again, the StatCrunch procedures here. Let's look at another example. This one says the tar content in 100 millimeter cigarettes is known to be normally distributed. A simple random sample of 25 filtered 100 millimeter cigarettes is obtained, and the tar content of each cigarette is measured. The sample has a standard deviation of 4.2 milligrams. Use the alpha equals 0.05 significance level to test the claim that the tar content of filtered 100 millimeter cigarettes has a standard deviation different from 3.2 milligrams, which is the standard deviation for unfiltered king-size cigarettes. I don't smoke. I know nothing about cigarettes. It just seems like there's so many varieties or something. But anyway, let's answer the question. Okay, so we want to test the claim that the tar content of filtered 100 millimeter cigarettes has a standard deviation different from 3.2. So we want to know if the standard deviation is different from 3.2, so not equal to 3.2. My family got home now. Everything's so noisy all of a sudden. I don't know what my dogs are going crazy about, but okay, so there's the alternative that we're trying to test. So then the null hypothesis is, of course, again, a statement of no change, no effect, no difference. So the null hypothesis is that, no, the tar content of these filtered cigarettes is the same as it is for the unfiltered cigarettes, which would be kind of strange, I think. But anyway, but this is what we're trying to test. Now, what sample information do we have to test this claim? Hey, look, I'm recording the video. Okay, so the sample information that we have is that the sample standard deviation, it says, was 4.2 milligrams. Okay, that is different from 3.2. It's fairly different. Is it different enough? Well, to know that, we have to run the test, right? So we're going to go to stat, variant stats, one sample with summary. We're going to be prompted to enter the sample size, which was what? It says a simple random sample of 25 filtered cigarettes. So N was 25. And then we'll be prompted for the sample variance, right? So the sample variance, S squared, is going to be 4.2 squared, right? So let's go to StatCrunch and see what we get. So it's stat, variant stats, one sample with summary. Sample variance is 25, or sorry, no, that's the sample size. The sample variance is 4.2 squared. Sample size is 25. And then our null and alternative hypotheses. So the null hypothesis is that sigma equals 3.2. That means sigma squared is 3.2 squared. The alternative is two-tailed, right? So we want to leave this as a two-tailed test. And there's our p-value, 0.0305. So the p-value, 0.0305. We can use that now to make our decision. Okay, so in terms of an interpretation, we can say something like this. If we assume that the true standard deviation is 3.2, then there's only about a 3% chance that we would get a sample standard deviation of 4.2. It's pretty unlikely that that would happen then, right? There's only a 3% chance that it would happen. So that casts doubt on the assumption that we made in the null hypothesis. It casts doubt on the assumption that the population standard deviation is 3.2. So we reject that assumption, right? So our decision is reject the null hypothesis, right? Since our p-value is small. How small? Well, less than alpha, right? So it's small enough. Okay. So in conclusion, we would say something like this. At the alpha equals 0.05 level of significance, the evidence suggests that, well, we're rejecting the null hypothesis, right? So the evidence suggests that the alternative must be true, right? So the evidence suggests that the standard deviation, tar content for filtered cigarettes is different from 3.2 milligrams. Right? So the standard deviation tar content is different from 3.2 milligrams. So the standard deviation tar content is different for these filtered cigarettes than it is for the unfiltered ones, which is probably a good thing. Anyway, that's that. I want to give you one more example, just because this one, on this one, we're given the raw data. So I wanted to run through an example where we go to with data instead of with summary. So let's do it. It says the standard deviation of the weight of fun-sized Snickers bars is 0.75 grams. The quality control engineer recalibrates the machine in an attempt to create the candy bars with a more consistent weight. The data below represent the weights in grams of 11 randomly selected fun-sized Snickers bars that were produced after the recalibration. Did the recalibration result in more consistent weights? Conduct the appropriate test. Another thing that I like about this problem is they don't ask you to, they don't say like, test whether the standard deviation is blah, blah, blah. They're asking the question a little bit more subtly than that. They're saying, did the recalibration result in more consistent weights? Well, so let's think about what that means. If the weights are more consistent, then there's less variability in the data. If there's less variability in the data, that means the standard deviation would be smaller. So more consistency means smaller standard deviation, okay? So we were told that the standard deviation before the recalibration was 0.75 grams. Now we want to know what's the standard deviation after the recalibration, and is it smaller than 0.75? And if so, is it different enough for us to conclude safely that the recalibration was successful, right? That the recalibration resulted in more consistent weights. So this is the hypothesis test we're going to run. We're going to say the null hypothesis is sort of the Debbie Downer, right? The null hypothesis is that, nah, it didn't have any effect, right? The standard deviation is still 0.75 grams, just like it was before. Okay, So the null hypothesis is that the standard deviation is 0.75, just like it always has been. The alternative hypothesis is that the standard deviation has decreased, right? Because we want to test to see if we had more consistent weights. More consistent weights would mean a smaller standard deviation. So we want to know if sigma is now less than 0.75. We don't know what the sample standard deviation is because they gave us the data instead of a summary. So we'll just have to feed this into StatCrunch to see what we get. So let's do it. We're going to go to stat, variance stats, one sample with data this time. Okay, so let's take a look. So I'm going to enter the data in here. So it's 19.68, 20.66, 19.56. I'm going to stop reading. Okay, and let me make sure I got those in there correctly. 19.66, 20.66, 19. Okay, looks good. So let's go to stat, variance stats, one sample with data. We tell StatCrunch where the data is stored. We tell StatCrunch what hypothesis test we want to run. We want to test to see if the null hypothesis is that sigma equals 0.75. If sigma is 0.75, then sigma squared would be 0.75 squared. And then the alternative is that it's a left-tailed test, right? So we hit compute, it gives us the p-value. It also gives us the sample variance, which is useful. So the population variance that we're assuming under the null hypothesis is 0.5625. The sample variance was 0.41 and some change. So the sample variance is smaller, and that means also that the sample standard deviation is smaller than 0.75. How much smaller? Well, not enough, right? We're 30% likely to have gotten this sample variance if the null hypothesis were true. That's not rare enough. It's not unusual enough for us to reject the null hypothesis. It's not unusual for us to think that, oh, maybe the null hypothesis isn't true, right? So we're not going to reject the null hypothesis here. So the p-value, 0.30, I think it was 3.3055. Let me double check. Oh, 0.3022, sorry. Oh, come on. 0.3022. Okay. So, as we said, that's not small enough, right? So we can say since 0.3022 is not less than 0.05, we do not reject the null hypothesis. So in conclusion, at the 0.05 level of significance, there's not sufficient evidence to suggest that the recalibration resulted in more consistent weights. Okay. So unfortunately for this particular quality control engineer, his recalibration didn't really help anything. What else was I going to say about that? My kids are so distracting right now. I apologize for all of the background noise. What else was I going to say? I can't remember. Must not have been that important. But anyway, that does it for that one.